right. We're doing the ECG demo board for Texas Instruments. I'm Justin Bohr. I'm a computer engineer.
I'm Nate Kesso. I'm an electrical engineer.
I'm Charlie, and I'm an electrical engineer.
I'm Mike Mack. I'm also an electrical engineer.
I'm Yuan Wei. I'm also
I'm Xie He, I'm electrical engineer.
So I'm going to give you a little background on what an electrocardiogram is and also the project that TI has presented for us. So an electrocardiogram, also known as ECG or EKG, what is it? An electrocardiogram is a device that measures the electrical activity of the heart. This electrical activity is generated by what are called biopotentials. Biopotentials are basically electric potentials between living cells. Basically, cells act like little batteries with positive and negative ion concentrations inside and outside of the cell membranes. When there is a disturbance in these biopotentials, that gives rise to the phenomenon known as action potential, which is the depolarization and repolarization of the cell. Essentially, action potentials are what ECG signals are. And this figure here shows that the final ECG signal is basically the superposition, or all these action potentials at the different nodes of the heart superimposed upon each other. There are many methods of measurement of these ECG signals. A common one that I want to introduce to you guys in this figure is the three electrode method. We have a positive electrode, which is placed on the right side of the heart, a negative electrode, which is placed on the left side of the heart, or I'm sorry, the positive electrode is on the left side of the heart, and the negative electrode is on the right side. And then we have a ground reference electrode. The reason we have the positive electrode on the right side of the heart, on the left side of the heart, sorry, is because the depolarization occurs on the right side of the heart. So as this depolarization wave propagates towards the positive electrode, that gives us the positive rising edge of the signal. And then, as the repolarization occurs, the ECG signal drops back down. There are many applications of ECG electrocardiograms. Their cardiologists use them to diagnose their patients with irregular heartbeats or heart diseases. Vets can use them on animals for the same diagnosis, and it's also used extensively in research. So TI has an old ECG board. This ECG board is outdated in that it has old components that are no longer a part of TI's business portfolio. It's very large, as you can see here. Relatively large, as you can see here, and it's not very accurate. It's also not mobile in that you have to connect the output to an oscilloscope. So our goal is to design and fabricate a demonstration board that is reliable and accurate, it's compact, sturdy, and we want to populate it with modern components. We also want to pair it with the Stellaris oscilloscope module, which is this board here. It has an LCD screen that can display the ECG signals, thus making our new board more mobile. After we've designed and fabricated this board, TI will use it to showcase to their potential customers as well as demonstrations.
This is our project timelines. The process of our project is divided into 3 phases. So for phase 1 is to design analog front-end circuit. The analog front-end circuit is our major ECG circuit. And the circuit we got is incomplete and outdated. So the first goal in phase 1 is to complete our schematic circuit by adding the power supplies, amplifier, and filters, and measuring the value of components. And after we complete our schematic circuit, we will put our schematic circuit into the Tina TI and to simulate it to see if it works. And according to our schematic circuit, we can design our PCB layout in PCB Artist. And both the Tina TI and the PCB Artist tools provided by TI. And once we got our PCB board, we can head to phase 2, which is pretty much to test our PCB board. First of all, we are going to test and compare our cardio simulators from TI, which is our input, to see how does the cardiac signals looks like and how much noise that they have. And then we are going to integrate our PCB board with the simulators and the Solaris microcontrollers to test the overall project. And this is pretty much our project, but we still have a phase 3 there, which is to design our design final project, the product, which means we are going to add extra functions to our ECG board to make them more competitive on design days. So right now, for phase 3, we are planning to allow the real-life signals go through our ECG board by the finger measurement and programming our microcontrollers to detect the diseases or beat per minute of the real-life signals. And if we can finish the phase 3 one step ahead, we can still add other functions to our ECG board.
I'm going to talk about the tools and resources that we have to accomplish this project. The tools that we use for the PCB layout design is the PCB Artist. And it has some features. First of all, it's free, and it provides a pretty intuitive feel for customers to use. And it has really automatic schematic to PCB transmission wizard, which helps the transition from schematic to PCB happens automatically. And then it has another advantage that we benefit a lot from during the process of designing, which is it has a really strong base of components libraries that allows us to control the variable of specific components that we have to implement the circuit. And then for the resources that TI provided us, first I want to talk about the Solaris microcontroller and oscilloscope demonstration kit, which is going to be used to display the output of our analog front-end signal. And the other thing is the cardio simulator 2, which will be used to generate simulate the real cardio signal in order to test the functionality of our front-end circuit. And the tools that we use most is the TINA TI, which is a pretty excellent circuit simulation tool based on SPICE. And compared to other SPICE tools, TINA TI features on its easiness to input the circuit as a diagram, and it can provide all kinds of analysis that we need. We also get important circuit parts provided from TI, such as the IMA33 that we use a lot in our front-end circuit.
For design consideration, our team's goal for the final product is to be a high reliability, low cost, and visually appealing to our customers. Also the most important thing, we want our final product, the ECG demo board, to be high integrity, which is very important for, as Nate said, the ECG signal is the signal from the heart. So if our ECG signal has very low SN ratio, as you can see from this curve, there is a lot of noise on this. So it's really annoying, especially for the doctor want to diagnose the illness of the patient. So our final product should have a very high resolution image of the ECG signal. How we gonna achieve these goals? It depends on how we use the op amps and how we do the layout on the PCB design. So next I'm handing to Mike.
So, as Yuan was saying, one of the most important things for our design is that we have a clean reference voltage. And we're using a battery, a 9-volt battery and a buck converter to buck down to 5 volts to deliver a low power application. One of the challenges with using a 5-volt single supply is that we have to bias all of our signals between our ground and our 5-volt references. And because of this, this 2.5-volt reference is what our input signals and our output signals are riding on that DC level. So any noise on this 2.5 reference voltage will carry through to our output signals. And in lab already, we've been experimenting with different ways of filtering that signal and getting a clean reference. And it's just further shown that it's really important to have a clean reference. Main causes that could give us bad signal integrity would be poor input filtering and also poor output filtering. And what I mean by that is in our design that Justin will touch on, we have RC networks on the inputs that have common mode and differential mode filtering. And then on our output, currently for our design, we have a simple inverting low pass filter to filter out high frequency noise. Our main instrumentation amplifier for our analog front end is the INA333, which is an integrated circuit of a simple instrumentation amplifier. It has some pretty good features: low noise, high common mode rejection ratio. And so some of the goals for utilizing that component are linear amplification, which ties directly with avoiding saturation of that op amp. And to do that also, it also ties with our reference voltage and also the filtering of the noise, because any noise riding on signals that can go up into the, either swing down to our 0 volts or up to our 5 volts will cause the op amp to saturate. And currently for cost for our project, our main cost is $33 to order a 2-layer PCB. And we've already ordered our first PCB and designed it, and so that's the major cost to our system. So one of the considerations is to keep our iterations of our design that we're doing down to a low number to avoid spiking up our costs for our project. Some other costs that we've incurred so far are ordering surface mount components. We just put in our order for our first board, and it was around $28 for all the parts. Another consideration for ordering parts is that we don't have access in the ECE building or ECE floor to like surface mount components of a whole variety of values like we do with through-hole components in the labs. So when we're designing our circuits and picking component values, we have to ensure that we order a wide variety of things that we could experiment with different gains or different filter cutoff frequencies to ultimately get the best result on our output signal. Shown here on this figure is an example that we've already filtered on our output from our CardioSim. And this is an example of the CardioSim signal, and we're comparing it to the Agilent signal generator cardiac waveform. So as you can see, there are some differences. The Agilent signal is much more precise. Just note that. And then the buck converter that we're using on our first board design is the TPS 62120, which this is from the application note from TI's website, and which helped us design our buck converter circuit.
All right, this is a block diagram for a circuit. On the top, we have the power. So on our PCB, we kind of separated this so that we could test it. It also, we separated the grounds because from the MOSFETs and the buck converter, there can be a lot of switching noise, which can affect our signals. So we separated those grounds. But we'd have a 9-volt battery that would go to the buck converter. And then to get a really clean 2.5 volt signal, we divided it to get down from 5 volts to 2.5, but then we have a low pass filter to clean it up. As for our ECG circuit, we have either the CardioSim or later when we get the finger sensors that we can get an actual ECG from anyone who walks up to the demo board and puts their fingers on it. And we go into some input filtering, which would be an RC network, to try and get rid of high frequency noise. Anything above the like 50 to 60 hertz range, we want to get rid of that power coupling that bodies can have at 50 or 60 hertz. And then the ECG signal is around 2 to like 3 hertz, so that's where we're focusing. From that, it would go into the INA 333, which this servo loop acts as a filter for getting rid of DC drift. It's a low pass filter and an integrator, which will feed back into the reference pin of the INA 333. Which will act as overall with the INA and the servo loop, will then become a low pass filter, or a high pass filter, getting rid of the DC. It'll pass through the 3 to 10 hertz, somewhere around there, through the INA and amplify it. From the INA, there's 2 pins for the gain, so you can set the gain through a resistance, and if you split that in half, and get that voltage, it'll give you the common mode voltage, which will feed back through a right leg drive, which will invert it and amplify it and send it back to the body or the cardio sim, which will help raise the reference voltage of whatever this may be, a body or the cardio sim, to 2.5 volts, so that our input will be at 2.5 volts, which will help with getting the signal. This will also help cancel out common mode interference, since we are inverting it and sending it back. So that it will decrease any noise that we get coming in from the body. After the INA, we have some post-filtering. We have an option of an RC network, but in testing in the lab, it wasn't doing much for us, so right now we might not use that, but we also have some active filtering that'll actually add an additional gain to it. So, because the signal coming in is around 1.5 millivolts peak to peak, and so we want an output that's around 2 to 3 volts peak to peak, so you need a gain of about 1,000, I think it was. So then after it's done filtering, we're going to send it to the Solaris oscilloscope, which is has an app running on it that you just input the ground and the positive voltage, and then there's a little screen, the LCD screen, that it will pop up on that you can see the waveform. This is our schematic from PCB Artist. This is we separated for this stage, phase 1, we separated these things with test points so that we could test each individual circuit to make sure everything was working. Later designs will connect it all together to be one full circuit. Right here we have the INA with the gain setting, the splitting of the common mode voltage that will then go to the right leg drive, be inverted and gained up a little bit and then sent back to the body. This would be the servo loop that goes into the reference pin of the INA. Out here is the RC network that we might or might not use. This is the active filtering and gain that we have after the INA. This would be our power circuit. This is the TPS 62, whatever the number is. And then after that, around the buck converter, you have to set its switching and all the settings for it with this circuitry around it. So we have an inductor and other things around here. And then through here we have the divider and a little bit of filtering with the capacitors, which will go to this filter, and that's where the 2.5 volts will come out, hopefully as clean as we can get it. The solutions we put in place to take care of all our design considerations, like I talked about earlier, is this filter for the 2.5 volts to output that as cleanly as possible, and then our servo loop to get rid of DC drift and any noise from the INA. This is just some pictures from our testing. This is, we ordered the parts in advance. Not all the parts on this board are exactly what we're going to use, because midway through we decided to change parts so that they can have interchangeable parts with the same footprint, so they can use this demo board for any line of op amps that they have, whatever they want it in place. So we have an INA 333, one version of an OPA 333 for the right leg drive, or actually 2 of them. And then we have just 2 741s, but this is pretty much our entire circuit, and we got it to work. as this is the output from that circuit, getting a noisy signal from either the ECG simulator or the Agilent waveform. Transferring this to PCB, this is what our PCB looks like for phase 1. This board is about 2.5 inches by 2.5 inches, so if you compare it to the older board, it's at like 15% of the size of the older board. This is also being able to transfer, so this is the actual board that we'll use for the oscilloscope, the Stellaris oscilloscope, and this is an actual reading from what we got from our test board here on the LCD. So as you can see, we've been able to do what we were tasked to do so far, and if this were to work, then we are done with phase 2, and we're looking to go to adding sensors for fingers that we don't know exactly how that's going to work yet. We're getting things to test, we've ordered those, and that we just need to finalize. As you can see, this is where I separate the ground. So we're going to test that buck converter, make sure it works with a 9-volt battery, and then we can make a plastic, part to one of those plastic things to hold the battery, and then finalize our circuit.
To summarize, we have talked about the ECG signal, especially its purpose is the signal from the heart. Also, we talk about our project timeline. In phase 1, we got to design analog front to end. In phase 2, we're gonna hook up it to the Stellaris microcontroller with the LEDs. In phase 3, maybe we can add on more features like the finger sensor or touching pad. Also, we're talking about tools and the results. We use TIT now to do the simulation, and use PCB artists to do the printed circuit board design. For design concern, we talk about the budget. We want our final product to be high reliability, low cost, and also has a high integrity of the ECG signal. For the design solution, Justin talking about how we design, simulate, fabricate, and test it, stuff like that. So basically, that's our design. So anybody have any questions?
Thank you.